just tell me I need more storage. Does anyone put videos on YouTube?
Luke does.
They take up a lot of space.
Doesn't Brad like fast?
You're seeing them sheaving. Right.
Probably not.
But then there's Lunker Luke. Oh yeah, Lunker Luke's the best. Lunker Luke. Yeah. Lunker. I'm the one that you want to watch. Yeah. That's why everyone goes there to watch me. Brad.
How's it going up there, Andy?
Well,
Is it recording?
Luke, if you want to learn something, you go.
Yeah.
If you want to just have a good laugh, you watch Brad. Yeah.
All right.
Videos are really funny. No, they definitely are.
Okay, so it's a 2x4. But what I do is I use a 2x4 and this little piece of wood. It's a very, very, very small scaled down version of a child's ride?
Teeter-totter.
Yeah, teeter-totter. Or,
Those are dangerous.
what are they called? Another word? Seesaw, right. So, so I kind of made this thing here. And I don't know if I'm going to be able to get it to balance, but that's okay. So, here's the concept. And I want everyone to kind of look up here. So, imagine this is a seesaw. Someday I'll probably end up making something that's a little bit higher or bigger so you can see it easier. But you guys understand the premise of this. And if we are sitting on this end, those people go up in the air. And if you're sitting on this end, and these people end up being heavier, then those people go up in the air. So, the concept is reactants are over here, products are over here. Equilibrium reactions have a lot to do with a seesaw, or a teeter-totter as it's called. But the hard thing to understand a little bit with this is in real life, you have people on this side, and they fall, or they go to the ground, they push off, they fall to the ground, they push off, whatever. And that's kind of how kids play on it, or that's how it works. In chemical reactions, we're going to actually be taking reactants and products and then sliding them on here. So sometimes reactants can slide over and form products, which will cause it to do this. Sometimes products will form reactants, which will cause it to do this. So, is it good to go?
Yeah, fixed it.
All right, good. Appreciate it.
Snaps it the other day.
It's not bad, actually. All right. So again, I'm going to explain a little bit better what the heck equilibrium means, but we're going to be using this next couple days to kind of help you understand how reactants and products can shift during a reaction. So let's first, I'll define it in a minute. Let's first talk about the different types. Phase changes is an example of an equilibrium. Now, I've defined this before. I've talked about it before. What happens during a phase change? When something melts, freezes, boils, condenses. What's happening? Do you have one phase or do you have two phases during a phase change? You have two. So, let's use an example. If you have H2O solid and it melts into H2O liquid, as it is melting, it is also solidifying at the exact same time, or freezing. As long as this is at 0 degrees Celsius, temperature is constant, you will have a slushy of sorts, solid and liquid at the exact same time. That's called equilibrium. It's only at 0. What happens if it drops below 0? We're all solid, no liquid. What happens if it goes above 0? All liquid, no solid. So if you keep the temperature held at 0 degrees, what you have is called equilibrium. What the heck is equilibrium? It's where you have one change and another change happening at the exact same time. That's called simultaneous, right? They're both occurring at the same time. This is my revolving door analogy on a hotel, or in a hotel. You got people going in, people coming out at the exact same time. That's what equilibrium is. Okay, we'll write the definition in a minute, but that's an example of a physical equilibrium where you have freezing and melting at the same time. What about boiling? What's that take place at? What temperature?
100
For water, what'd you say?
For water?
Yeah, 100. So 100 degrees Celsius would be H2O liquid. Put a double arrow, one going one way, one going the other, and then H2O gas. That would be another example of a physical equilibrium. Another example that we've used before, I'm just going to draw it here and then erase it so you don't have to put it down. But if you have water and you cover that and you boil it, so you add some heat, you have evaporation, and then what's the opposite? Condensation. That's called dynamic equilibrium. We've talked about that before, and the pressure up here builds, and then you have vapor and liquid at the same time. That's called equilibrium as well. So I'm just refreshing your memory on things we've already discussed, and it's not completely new, not a total new topic here. So that's physical. Why is this physical? Why are phase changes physical? How come they're not chemical changes? Doesn't change what? The composition, the bonding, right? You still have water. So it's just a different state, right? Chemical reaction would be something like the formation of ammonia. N2 gas plus H2 gas, write this down, yields NH3 gas. And we have to put a 2 and a 3 here. That would be a chemical reaction that we say is at equilibrium. What does that mean? It means every time 3 hydrogens and 1 nitrogen form 2 ammonias break down into 3 hydrogens and 1 nitrogen. They're literally happening at the same time. That's called equilibrium. When 2 things happen at the same time. 2 things happening at the same time is called equilibrium. I'm going to say that a lot the next couple days because I need you to burn that into your brain. What is equilibrium? 2 things occurring at the same time. Or, what did we just learn about? It was a short, quick unit, the kinetics. What were we talking about most of the time? What was the main idea? What was the big potential energy diagram? What was the homework last night about? You had bookwork, I think, a while ago. I wasn't here. It was about this. What was the unit called? Flip back. You're losing your mind. It was just before break, a week before break. Kinetics. What was the first thing we started talking about? Rate of reactions. Everything we talked about had to do with rate of reaction. What affects the rate? The collisions. That was the gist of it. All right? Now, back to this. Back to this. Stay with me. Stop talking. The rate of the forward equals the rate of the reverse. That's the book definition of equilibrium. It's when the rate of the forward process equals the rate of the reverse. Think about what that means. It means this is going to go this way just as fast as this is going this way. These two are going to combine to make this just as fast as this breaks down into those two. That's equilibrium. 2 things happening at the exact same time, or a better way to say it, 2 things occurring at the exact same rate. That's what equilibrium is. I wanted to start off the conversation with examples that you've already know and talked about, and we've seen that reaction before. All right, in lab, yeah, it's hard to show equilibrium. All right, I can actually show you a demo, maybe in a couple days, but it's still hard to really visualize and understand. So it is better to actually use equations on the board, but I'll show you a demo too. But that's what equilibrium is. Double arrow, 2 things occurring at the same rate. What does this word mean, reversible? What does that mean? It can go backwards. It can go the opposite direction. So this is always going to be forward, this is reverse. Reactions that are reversible are said to be, or can be at equilibrium. Alright, so let's define that word, and then we're going to learn a French term called le châtier. Anyone take French? One person in here?
I took French.
It's okay. So here's the definition. Underneath that, write this down. A situation, we'll say situation because it can be chemical or physical. A situation or scenario, we could say, at equilibrium is one where 2 processes are occurring at, I can never spell that word, the same rate. What is it, 2 R's?
Yeah.
I had that conversation like 5 times a year.
Oh my gosh, I'm gonna spell equilibrium wrong. Forever.
Well, are you spelling it like equal as? Yeah. A situation at equilibrium is one where 2 processes are occurring at the same rate. The forward rate equals the reverse rate. That's very important. That is the definition of equilibrium. Now, as a result of this here, the rates of the forward and reverse, as those are becoming equal, the rates of the forward, rates of the reverse, what the result of that is, put a little star here, the concentrations of reactants and products are constant. I'm going to explain that again before I move into the French term there. The Chatier. Kind of a big deal with Chatier. That's what we're going to use the 2x4 for. Bless you. Bless you. I got to get some weights here. So the forward rate equals the reverse rate. The concentrations of reactants and products are constant. I'll explain that in a second. Let me let you finish writing that down. And I think I'll get the magnets out to help you visualize. We're good?
No.
No.
Okay.
Okay. You sure?
Yep.
Alright, so let me use a different example here than the one we just had. Let's use, bless you. You know what? We could actually use formation of water. Let's go H2 gas, write this down please, plus O2 gas. Reversible here, 2H2O gas. And we're going to need 2 of those. Okay. So what I'm going to try and show you here with the magnets is what that last thing we wrote means. What do I mean they stay constant? I'll explain that. Alright, so let's use the red and the yellow. Alright, so we'll do red for hydrogen. So there's 2H2. And there's 1 O2. And we need 2 of these. Alright, so here's what happens. So at equilibrium, if this is at equilibrium, so I give you this reaction, I say the following reaction is at equilibrium. What does that mean? It means the rate of the forward is equal to the rate of the reverse. What does that mean? It means these are forming water at the exact same time water is breaking down into those two. They're occurring simultaneous. Now, how many reactants do we have? How many reactant molecules are, I could say how many moles of reactants do we have? 3. 2 plus 1, we have 3 moles. Everybody good? 2 plus 1 is 3? Learned that a long time ago. Okay. How many moles of products? 2. Does 3 equal 2? No, 3 is bigger than 2. Yes? We agree. So at equilibrium, this is very important. Listen, please listen. Clear your mind of any other stuff you're thinking about. Very important. At equilibrium, the amount of reactants, aka the moles, and the amount of products are not necessarily equal. Kids have a hard time with that because they write equilibrium, they think equal. Things should be equal. That's not the case. This proves it. There's 3, there's 2. 3 does not equal 2. You know that. What is equal? It's how fast they react. That's what's equal. It's reacting and it's breaking down at the same time. That's what's equal. The concentration, stay with me, the concentration, what is that? The amount of each. That isn't equal, it's constant. What does constant mean? How is the word equal different than the word constant? Think about it for a second. I had a big conversation last year with one of my classes. A couple of the kids were trying to tell me those 2 words mean the same thing. And I kept, don't say it yet, I kept giving good examples and explaining how they're different. Most of the class got it, but a few kids really were stubborn about it. So I want to make you guys think of it on your own. How is the word equal different than the word constant? Because I think they're very different. And then you got to relate it to this. You want to give it a shot?
Not anymore.
Not anymore. Okay?
Constant is like, it's one value that will always stay the same, and equal is two values that are the same amount.
Say that again. I like that. That was good, Kai. Say it again. Constant means one value.
One value that will never change.
One value that doesn't change, so it stays constant.
Yeah.
It doesn't change. Good. But equal?
Equal is two values, or two or more, that are all the same quantity amount.
Good. Good. So equal would be two or more values that have the same amount or same quantity. Good. Now relate it to this. How are these amounts constant but not equal?
The number of atoms doesn't change, but the number of moles does, I guess.
That's really confusing. So let's not say it that way.
Okay, what am I going to say there?
Well, that's what I'm asking you. I don't know. It's hard. How do I know that these amounts of reactant, 3 moles and 2 moles, are staying constant? How do I know that if it's at equilibrium? This is not an easy question. The way I know is because the rates are equal. What does that mean? Every time, here's what happens. It's hard to show you. I'm going to show you, but stay with me. Every time these two come over here and form 2 waters, what's happening at the exact same time? These two are breaking apart. Did anything change? No. So then it does it again. These two come over here and they make water at literally the exact, I can't do it at the same time, especially with only one good arm here. But at literally the same time, these will break apart and they will form the original reactants. And it just keeps going back and forth, and those two happen simultaneously. That's the difference between constant and equal. So the fact that these 3, right, but these 2 reactants are forming water at the same time that these 2 are forming the reactants, that's equal. Their speed is equal. What's constant is I always have 3 moles here and 2 moles here. How do I know it's constant? Because they're switching at the same time. So every time this disappears, this fills it in. Every time that disappears, this fills it in. So it's constantly going back and forth. That's the important concept here. That at equilibrium, because they're both moving literally at the same time, nothing ever changes. Nothing ever changes. Okay? So imagine we have one person standing here that weighs 100 pounds, and one person standing here that weighs 100 pounds. What was that? Am I hearing things?
No.
This is binder, the careful.
Oh, all right. I sound like glass breaking. I'm like traumatized from lab. I broke like 8 glasses. So let's say one person 100 pounds here, one person 100 pounds here. Would they be balanced? On a seesaw, right? They would be balanced like this, right? Now, if I wanted to keep this balanced, but I wanted to move them, what would I have them do?
Move them to the center at the same rate.
Imagine that there are tiny people standing on this right now. I have one tiny person here, one tiny person here. And I want them to move, but I want this to stay balanced. What's the only thing they can do?
They step towards the center.
Step towards the center, right. So what I'm trying to get you to understand, I really wish I had 2 hands here. If this is balanced, okay, constant, they're constant, the only way to keep that balanced is if they both switch at the exact same time. And if they switch at the exact same time, it will stay balanced. But the analogy breaks down if you take it literally. Because the amount here will not always equal the amount here. In real life on a seesaw, that's kind of how it works. But in chemical reactions, it isn't. So it's hard. You have to kind of think a little bit harder than just taking it as a literal example. But in order to keep these constant, the only way to keep 2 here and 1 here and 2 here is if they switch at the same time. So I'm spending a lot of time and energy trying to get you to understand. And the only thing I want you to understand today, the bell's going to ring, is that at equilibrium, the 2 rates are equal, which keeps both sides constant. That's what I want you to understand. So we'll pick that up tomorrow. I will be after school, And that's it.
Could you imagine a little tiny person being 100 pounds?
Yeah, I guess I should have said 100 grams. Maybe they are really dense. Maybe they're made of, what's Wolverine's thing? Adamantium? You're not a Wolverine fan?
I haven't watched any of those movies.
Well, you're missing
Probably
out.
should.
What's up? Okay.
You don't have a bag, do you? Anybody have a bag here?
No, I use them all. Quadruple.
You add 10, it's double. The original one is 10. If you add 20, it'll triple it.
Hold on. Hold on. Where is my marker?
Well,
No.
wording. I left a calculator here, graphic calculator, during lab.
Like one of these guys? Not this, but very similar?
It's a TI-84, you know the ones that have
Yeah, but I mean, you got a screen and...
yeah, screen.
I was in there period 8 with class, but then I left right at the end of the day. I left at 2:30.
Yeah, isn't there like a calculator bucket or something?
Yeah, but I don't... You can check it. I don't think it's in there. Here, let me explain. I just had a marker. Okay. So, here's the deal. You got temperature,